Hello viewers, and welcome back to another session of emulating RISC-V in a high-level language. In the previous sessions we've been talking about slowly moving the encoding to actually match the words that are interpreted as machine code by the RISC-V processor families. And we're going to continue doing that, and today the turn has come to implementing branches and jumps. But as a stepping stone, we're also going to implement loads and stores, which were previously implemented in our emulator, but now we need to implement a proper assembler and a proper decoder for them. So let's jump right into this. So the emulator is supposed to be able to handle this little program, which, as you may recall, computes the factorial of an integer. And the only instructions that we have left now really are these two control flow instructions, the goto, which actually isn't called goto in RISC-V, but we'll get to that later, and the B and Z, which also isn't called that in RISC-V. But again, we'll wait until we're ready for them. The challenge of these instructions is that there are some new concepts that we have to learn, and also that we have to be able to assemble instructions by picking apart these immediate numbers into smaller pieces. And I'll explain shortly what I mean by that. But first, let's switch back to the manual, which will tell us a little bit about the instruction types that we're supposed to be able to decode with our emulator. So you may recall that the instruction words, the 32-bit words that describe a particular machine code instruction, have different formats on RISC-V, just like on any other processor. And these are the major formats on screen right now. And we've already implemented partial support for R-type instructions, where there are two source registers, and then a result or destination register, and the operation that is executed by the processor is defined by the funct3 and the funct7 fields. We also implemented the immediate type instruction, where we have a source instruction or a source register, and then a pile of bits, which are the immediate value. This is not a register, but actually a numeric value that we then use this operation to operate on and put the result back in the register specified by RD. We're now going to run into the S-type instruction, and the S there stands for store, and this instruction is used by store instructions. Well, you might ask, where's the L-type instruction for loads? Well, it turns out that the L-type instruction is very similar to the I-type instruction. It takes a base register, which we'll use RS1 for, and then a signed offset, which will be the number that gets added to the base register. Then the RISC-V processor fetches the memory at that address and puts the result in RD. So we'll be able to reuse the I-type instruction for that. But when we're storing values in memory, we need two registers. We need the actual value that we want to store, which is RS2, and then the base register again, so where we want to, indicating where in the memory we want to store the word or the data. But that RS2 field is right in the middle of the immediate field of the I-type instruction. So the RISC-V designers decided to take the 5 bits that are no longer needed for the destination register and use those bits to store the immediate displacement of the store instruction. The problem now is that that field is divided up into two fields. It's not a huge problem though, and we'll be able to solve that. But this is our stepping stone, because the branch and the jump instructions get even more complicated. So let's start by looking at the encoding of the load instruction, because we'll want to do that straight away. And so if we find the load byte instruction, it looks like this. So as you can see, it's fairly simple. We take our base register, we add an immediate offset to it, and then we fetch it from the resulting data from, or we use the resulting address to fetch from memory, and then we store the result in the target register RD. And remember also that these LB, LH instructions are sign extensions. This means that if we load a byte, that is an 8-bit quantity from memory, then the remaining 24 bits get the same value as the highest bit of the byte that we just read, in effect sign extending it. And the same comment for the load half word, where loading a half word will load 16 bits from memory, and then we look at the highest bit of the 16th or well, bit 15 in the word that we read, and we copy that to all the remaining bits in the word. Load word will just load a word from memory, a 32-bit word, and no other changes are necessary on this 32-bit processor. And then in addition we have these two unsigned variants of load byte and load half word, which will do the same thing. They will read a byte from memory, but in this case they will zero extend the byte, correctly modeling unsigned numbers or unsigned integers. Storing bytes, half words, and words is quite simple. There's no need for an unsigned here, because what we're doing here is taking the lowest 8 bits in the case of store byte and the lowest 16 bits in the case of store half word, and storing them into the memory that is referred to by RS1 plus the immediate offset, which has been split up into 2 halves. And the source of the value that we're storing is in RS2. Great, so let's start by implementing LB, load byte, the signed byte. And so what we need to do is, as in the previous sessions, we have to create, we have to be able to assemble it, and then we have to be able to emulate it. Let's start by assembling. So we'll need a unit test for this. So let's grab this. And let's go to our project, and we'll run the, we'll add a new test to our assembler. And this test will be LB. So we take the bits straight out of the manual. And now we'll create an 11-bit pattern that is easy to recognize so that we can verify that everything is okay. We're going to make the high bit signed so that it will get signed extended. And then we'll put, well, I might as well copy the pattern from this instruction. This is all bits 1 except for the lowest one. So this should result in -2. Remember that to interpret this as a negative number, you take all the bits, you flip them so that all the 1s become 0s and all the 0s become 1s. So we get 0, 0, 0, 0, 0, 1, and then you add a 1 to give 2, or 1, 0 in binary, and that 2 is negated, so -2. This is a -2. And then the base register is going to be this register again, and then the function code is 0, 0, 0, so we'll just put those 3 zeros there. And then the destination register is going to be, we'll use the same one as the instruction above, making sure that we use all the bits in the range, the 5-bit range. And then finally, the major opcode at the end, signifying a load. So this is what we expect to happen when we assemble the following instruction. So we expect the -2 here to be moved into these 12 bits, and the 17 is the destination, which is these 5 bits, and the 21 is the base register, which is the bits over here in RS2. Fantastic. So let's go ahead and run this unit test, and of course it will fail because we haven't really implemented this assembler or assembly language for, or an assembler case for this particular instruction. Okay, so here we go. It's complaining about an unknown instruction. Fantastic. So let's implement then LB. I'll put this case in alphabetical order for the time being. And so we can piggyback on as am I. And then the major opcode was this value here. And the minor opcode was all zeros. And then destination, source 1, source 2. There we go. So that will do the byte load. Let's attempt to verify this. Looks okay to me. Since we're here, we might as well use the opportunity to load word and load half word. So we'll implement the load half word and the load word instructions. Just make sure that we get the right encodings. For the load half word, the funct3 field is 001. And, oh, wrong. This was 010. For the half word, it's 001. And it also turns out we haven't implemented load half word. Let's go ahead and implement that. And I'm also going to get rid of these initializers because we don't need them. The C# language will do that for us. So let's replace those with nothing. There we go. Okie dokie. So let's go back. So we have our load high and our half word, and then we have our load word. And let's run all our tests again. I'm expecting green bars. Oh, we have a failure on LH. Well, that makes sense, of course. We haven't actually implemented it. So let's do LH and LW. So LH was the 001 and LW was 010. Okay, one more try. Great. There we go. Great. So now we've implemented the signed loads. Let's go ahead and implement the unsigned load as well. And the encoding of LH and LB will be reused here, except that we need to use the funct3 fields for unsigned. So we'll need to implement those. And we'll need to add them to our mnemonics as well. At some point I'm going to tidy up this file. But right now these mnemonics are in a haphazard order. So here we go. We have LHU and LBU. And so for LBU, the 3 bits are 100, and for LHU they're 101. So easy, we just add a 1 here and a 1 here. And if we run all of our tests now, we now hit the missing instructions. So let's implement LBU as 100 and LHU as 101. And let's run these again. So now we've implemented all the loads that we need for a 32-bit RISC-V processor. Now we're going to focus our attention on stores. So let's go back to the manual and take a look at what a store should look like. So it looks like this. Let's grab this description for the store byte instruction, and then we'll hop over to our assembler tests and we'll add a test for store byte. So in this case, store byte recall that it has its immediate field broken up into two halves. So we need to do the same thing. And in this case, I would like to use a more complicated pattern, a bit pattern, to verify that we don't mess up the concatenation of the fields, because that's what we're going to have to do. We're going to have to take these 5 bits and these 5 bits and extract them from the bits that the user is giving us. So the bit pattern that the user is going to give us is going to be the 12 bits that look like this. That's 12 bits, and this is a negative number, and we know that because the 12th, the highest significant bit, is a 1, which signifies negative. And so we'll want to make sure that the result, in the resulting word, we'll get a pattern of A, and then possibly signed extended. So let's write the test for this beast. So the bit pattern is going to be, so the way this is interpreted is these are the 5 bottommost bits and these are the 7 highest bits. So that's 7 bits. So we're going to have to peel off 1, 2, 3, 4, 5, 6, 7 bits. That's the high bit. And then the same registers as before, but now we're going to need a source register. So let's use the source register 11101, which is that is 27. And then the funct3 is 3 zeros. And then the hold on. We need the RS1, the base register. That needs to go here before the funct3. Then the zeros for the store function, and finally the low 5 bits of the immediate word. We tack on the opcode, and now that is the expected output of our assembler when assembling a stored byte instruction. So let's assemble this. So the mnemonics is stored byte, and this is going to be now we need to go back to the manual and refer to how exactly the arguments are ordered. And this is a subtle point, but for the case of store, the instructions are not or the operands of the instruction are not ordered in the same way as in the other instructions. So let's find store, load store. Okay, so let's see, where can we find a description of the load? Okay, so RS2 is the source of the store, and then the destination is the offset plus x2. So we have to follow the pattern of we have to flip the order of the registers. So we'll use the same registers as before, but in this case 17 is the register whose value we're storing. 21 is still our base register, and then this bit pattern is, let's find out what the bit pattern is. It's going to be 101010 101010, and that's AAA. And if we change the sign of this, it's going to be minus 556. So minus 556. And we're expecting that minus 556 to turn into 101010 1010, split up into two fields. So this is the job ahead of us. Okay, so let's run our test and discover that we have not implemented the SB instruction. Okay, so let's start by creating a case for SB, and now we're going to introduce a new ASM subfunction, ASM S, where we take the major opcode, and the major opcode is I've already forgotten it, so let's just grab it from the source. This is our major opcode. And then we're going to need to store a funct3, which is, in this case, 3 zeros. And then we will take the destination slot, but in this case, the destination, well, the first slot is going to be what we want to treat as the RS2. So we'll pass it in, but we'll have to be careful to use it correctly in the implementation of ASM-S. You'll see shortly what I mean. So let's go to ASM-S. So we're going to rename this parameter. This is going to be source1, and this is going to be called offset. Sorry, source2. So this is the source of the instruction. Let's call this base register instead, just to make it clear what we're doing. Okay, and then maybe we can steal some code or get inspired by the code from the previous load I. So looking carefully at what we're trying to build now, we want to build the lowest bits should be these bits. So we'll say uint instruction equals the opcode. So now we have the lowest bits, and we'll call this opcode. This is our func3. Okay, so the next 5 bits are going to be the lowest 5 bits of the immediate value. That's easy enough. We will take the immediate value, which is offset, and then we mask it down. This extracts the lowest 5 bits, and then we need to shift it to the left by 7 so that we don't overwrite the opcode, which is already in the lower 7 bits. And then we need to turn this into an unsigned integer. And then we use the OR operator to merge that in. Great. The next piece of information that we need to push in are the funct. So we'll put that in there. uint stir func3 shifted light by 12. The next bit is going to be RS1, the base register in this case. So let's take the base register and we shift it. Well, first we mask it, and then we shift it by 15. And how do I know it's 15? Well, func3 is 3 bits. That's been shifted in 12 bits, so we need 15 for the next field. And now that field being 5 bits wide now puts us at position 20. And in position 20, we want to grab the high 7 bits of the signed offset. So what we're going to do is we're going to take the offset, and we've already consumed 5 bits of the offset, so we can now shift those out toward the out of the right side of the offset. So this will also sign extend offset because it's a negative number. So if it's already negative, it will continue to be negative after the shift. And then we now have our offset, and then that needs to be positioned in bit position 20 decimal. And we need to cast this to an integer. Okay, so that should do it. Then we need to write to memory and increment our pointer by 4. Let's give this a try. Okay, so we have a failure. This is not what we expected. So let's make sure that the binary bit pattern that we're getting, the -556, is in fact what we expect. So let's go to our assembler and put a breakpoint here, and then let's debug this one test. So the offset is -556, which in the calculator was, let's look at it again, 556 that's hexadecimal. Okay, so here I made a mistake. It's 556 hexadecimal negated, but that's minus this number. So let's copy this number and try this again. Yeah, it's very easy to get confused between signed and unsigned. We have to remember that this value is a decimal number. We could, of course, have written the hexadecimal number, but let's go with this for now. And let's try the unit test again and see whether we can get it to pass. We're taking our time. Oh, I think we're in an active session. That's why. Let's stop this and then run it again. Okay, so not quite there yet, but the lowest 5 bits are okay. There's something wrong with the high bits. So let's take a look at what -136 -136 is in binary, and it's a bunch of ones, which indicates the negative number, and then at the very bottom there's 1010, 1010, 1010. That's 12 bits. Let me confirm that that in fact is 12 bits. We'll go to the so that's 5 or 7, and that's 5. So we should have 12 bits. So we're doing something wrong in that case. All right, so let's take a look at what we're doing wrong. So let's look closely at the result of the test, and let's see what we get in the output. So we have our lowest 5 bits are correct, and then 1, 2, 3, 4, 5, 6, 7. So I am incorrectly placing these, I think. Let's take a look. Opcode first, followed by the base offset. Func3 is at position 12. Correct. The base register is at position 15. Correct. Oh, here we go. There's a mistake. So the source 2 we're not even using. So we need to put source 2 in its proper place, which is position 20, and then another 5 bits, putting us at position 25. That's where our bits are supposed to go. So let's give that another try. Make sure we are not running in the debugger. Here we go. Okay. Not quite what we want. What's the let's see what the problem is here. The output is slightly better, but the 1101 here is not showing up. So the 7 bits are correct. Okay. Let's remember that I'm mixing these up. So this is SR2 17. That is what ends up going here. Let's change this then to match the 17. We want the 17 to go there. And then this is the base register, which is 21. That is correct. Let's try that again. Almost, but not quite. This is 17. This is 21. Maybe we're doing another error in here. Base register by 15. Are we confusing ourselves here? We are taking the... This is what is going to end up in source 2. Let's go to ASM. Source 2. base register offset. Alright, I guess we'll have to debug this again. Here we go. So, source 2, our destination register is 17. Our base register is 21. Here is our base register 21 being shifted to the right by 15, and here's source register 2. Oh, another bug. These are not hexadecimal constants, these are binary constants. Yes, I feel a little embarrassed there, but you know, this is what happens when you're programming. You will make silly mistakes as well. Now finally, store byte is implemented correctly, and now we can jump in and finish this up and do the store half word and store word as well. So store half word, and store word, and the only difference here is going to be the bit patterns for the funct3 field. So if we go to store byte, that was 00, store half word is 001, and store word is 010. So we'll change this to 010, this to 01. I will also add a store half word up mnemonic, because we don't have one. Good. Okay, so now if we run this, we expect an error to occur because we haven't implemented the actual assembler yet, but we did all the hard work already for store byte. So all we have to do now is copy this case into two new cases, one for half word and one for word. And in the half word case, we will use the funct3 of 001, and in the stored word case it's 010. And with a little bit of luck, this should now pass all of our tests. Perfect. So now we have stores and loads implemented. Now let's take a look at branches. And when you look at branches, you might recoil a little bit in horror because they look really complicated. So here's branch not equal, and you'll notice how it compares RS1 and RS2, or rather the value in register specified by RS1 and the value in the register that's specified by RS2. And if the result is not equal, then we jump to a destination. Now first of all, we'll notice that the immediate value that we use to decide where we're supposed to go if the values are not equal has been broken up into little pieces, 4 little pieces. So we're going to have to do the same thing for our assembler. But secondly, there's a detail that I did not mention when I introduced the branch and jump instructions, and this is that in many architectures, including RISC-V, when you specify the destination that you want the branch to take if the condition is true, that destination is not specified as an address, but rather as an offset in memory from the current position of the instruction. So let's give an example. Get an example of this. So we go back to the pseudocode that we had, or the assembler code that we had for our previous factorial function. Recall that the goto function had an encoding where it said go to destination 5, and so we would say, where's destination 5? Well, it's 0, 1, 2, 3, 4, 5. This is the destination or address 5. But there's two things we need to take into account here. First of all, this 5 should really be addressing not an instruction number. Remember, this is instruction number 0, and this is instruction number 1, but it should be addressing a distance from the instruction itself and the target instruction, but the distance is not in the number of instructions, but in the number of bytes. So if you think of every instruction as having an address, this instruction starting at address 0, then this instruction is at address 4, because RISC-V instructions are 4 bytes wide, and then the jump instruction itself, or the go-to instruction, is at address 8. Now this instruction is going to be at address hexadecimal C, or 12, and then the next one is going to be at address 10, and then finally the instruction is 14. This instruction is the destination that we want to go to. But however, we could change this to hexadecimal 14, but this is still incorrect, because what we're supposed to be doing is taking the offset or displacement from this instruction to this instruction. So in this case, what we want to jump is a distance of hexadecimal 14 minus 8, which is 12, or hexadecimal C. A special case is if you were to write the following code. A displacement of 0 means that this goto goes to itself. This is an infinite loop. And naturally, you can have negative offsets. So a displacement of -4 would go to the address or the instruction that is previous in the instruction stream. So this would make a little loop that would just spin forever. So in this case, what we need to do is change this instruction, or in our little factorial implementation, such that it goes to the offset specified by this number here, which is 12 bytes ahead. So this really means go to the position that's 12 bytes ahead of my own position, which is 8 plus 12, which is 20 decimal, which is 14 in hexadecimal. So this is what we need to do. We need to take this number and then encode it in the appropriate way. Now, recall that there are two kinds of branches in RISC-V. There's the conditional branches, which we see here, and these will do a comparison of two registers, and if the comparison is true, they take a branch, otherwise they just fall through to the instruction that follows. Then there's also the JAL, jump and link instruction, which is the unconditional jump. You'll notice that it has a much larger field where it stores the destination. But sadly, this field is also not easy. It is quite jumbled up, in fact. You can see how the value that gets stored in this field first picks the high bit, the bit 20 of the offset, and then it goes and picks a few bits in the middle, and another bit from somewhere else, and then some bits a little bit higher up. So this is going to take a little bit of finagling to get right, but if you're very careful, we should be able to get this to work. So we have two instructions to implement: BNE and jump and link. So remember when I said we don't have a goto? Well, this is what it is. We don't have a goto, but we do have this instruction, jump and link. And we'll talk about link next time. For now, you can ignore link. Don't think about it, but we will be bringing that up next time. So let's not muck with the emulator just yet. We're going to go into the assembler and implement the branch not equal and the jump and link instruction, or we don't care about the link. And once we've done that, we've been able to implement these. So we're going to get rid of those now. We don't need to hang on to that little comment. So jump and link. What does jump and link look like? Well, let's first copy the template here. And we'll use it for B and E. So B and E will compare two registers and then make a jump. And let's make it a -4, which is this. That would mean a jump to the instruction previous to this instruction in the instruction stream. And we'll need to implement the mnemonic. And remember that this B and Z doesn't actually exist. Let's make a note of that, and we'll instead introduce B and E. And let's introduce, where do we have our go to? We will put a same comment here. And we will instead introduce jump and link here. Nice. Okay, so let's go now to the manual and see what a... Let's start with the branch not equal. I'm a little scared of jump and link because it's got so many different pieces. But we'll start with a branch not equal, and then we'll use our findings to work our courage up to the jump and link. So what do we want to have happen here? So we want the bottom 7 bits are going to be this major opcode. And then we have the funct3 field. 001 means not equal. Then we have RS1 and RS2. So RS1 is now going to be 21 and 17. This is 21 and this is 17. And then we have the jump. And my goodness me, -4 will be our destination. And that's going to make our life very easy because all we have to do is... Now, let's keep using the same number as before. This number here, the 101010 pattern, because we want to make sure that we're not cheating here. The 01010 will scatter among all these bits, resulting in a non-regular a pattern that does not look like 101010. So we'll keep using this negative constant to force ourselves to be honest. Alright, so let's grab this now. And this was jump and link. I'm not sure why I'm I'm not sure why I'm mucking about there. We'll fix this, no worries. I'm really not paying attention, am I? This goes here. Let's just grab this word and paste it here. There it is. And then for jump and link, goodness me, it's this beast. And we'll grab the major opcode. And the destination register, RD, is the link that I've been mentioning. I'm not going to go into details now. I'm just going to call that 0 for now. And then we have the bits of 1010. So let's see if we can do this manually. The first bit is going to be here. And then bits 19 and down to 12 are at the bottom. So how many bits are there in between? These are 10 bits, 11 bits. And then 0, 1, 0, 1, 0, 1, 0, 1. That makes 8 bits. So we have eaten 9 bits in total. Then the next bit goes here. And then the remaining 11 bits are 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. I have no confidence this was right. In fact, yeah, we had too many bits. And weirdly, our pattern looks looks unchanged. Could that truly be the case? Let's see. This is an odd number of bits. This 1 to 10, that's 9 bits plus 1, that's 10 bits, 11 bits, 12 bits, 20 bits. Yeah, this looks correct. Okay, well, this is our bit pattern. Insane as it sounds. No, that can't be right. There's too many bits. Well, let's start with this and let's see what happens. But before we jump into JAL, we're going to do B and E because this is a lot simpler. So B and E takes -4, and it's going to sprinkle that around this word. We're actually not going to use -4. We're going to use 1366 as I initially intended. Let's do that. Okay. Oof. All right, here goes. So this is going to be painful. All right, so it's complaining it doesn't know what B and E is. That was expected. Let's put this in alphabetical order for fun. And then now we need to implement a new instruction type. So before we had the R type and the I type and the S type, but now we need to implement the B type. So in order to implement the B type, we first need to get the, well, let's see. The B type takes the usual 3 parameters. So we'll write ASM B, and then we need the mnemonic, the major mnemonic for branch, which is this. Then we take the major, or the func3, which was, actually we have it already. It's in the unit test, and it is 001. This is the func3. So let's put that in its place. 0001. That's the func3, and then we have our 2 operands. The the naming here is confusing. I'm probably going to rename these operands. This is operand, the first operand, operand 1. But we're calling it DST for now. And the second operand, SRC1, those are the 2 register descriptors. So we're going to read the values that are stored in those registers, and then we're going to jump, if the condition is true, to the following displacement, SRC2. Okay. So, ASM B. So this is ASM B, and we'll change the first 2 pieces as usual. They're unsigned fragments. They're going to be plopped directly into the instruction. We'll start by initializing the lower 7 bits of opcode, or the instruction with the opcode bits. And then let's do the let's do the funct3 part. So we have that out of the way. Let's also do the registers. So the destination, which really is source 1 in this case, and then source 2, and this should be offset. Source 1 is going to be stored at position 115. So we'll take, in fact, we can do this. We can just steal this and rename this from base reg to source 1. And that has taken care of the registers. But now comes the hard part, which is the breaking up part of the offset and grabbing the individual bits and then assembling those pieces together in the jumbled order. Well, we have some tools to our disposal. The first of which is the bit fields that we introduced in a previous session. We need to create a few bit field objects to read the bit fields that we want. So we need the bit field for, well, let's start at the bottom. This is the lowest bit field. And this bit field is bit field that starts at position 1 and ends at position 4 inclusive. That's 4 bits. So I'm going to call it bit field starting at 1, length 4. The next bit field is this field, which starts at position 5. And then has a length of 5, 10 minus 5, plus 1. That's 6. 1, 2, 3, 4, 5, 6. 6 bits. So this one is called bitfit 5, 6. The next one is going to be the bit called 11. That's a single bit. So the bit field at position 11 of length 1. And then finally, bit position 12. Oh, what's going on here? There. So those 4 bits will pick apart the number that we're looking at and then give us the result, the resulting subfields. And then we have to assemble them in the right order too. So let's start with bits, same order, bits, these 4 bits, bits 1 through 4. So we'll say bits 1 through 4 are bit field 1 of length 4. And we're going to read, extract an unsigned bit field. And let's take the offset and cast it to an unsigned value so that we don't have to deal with sign extensions. So we'll say unsigned offset equals unsigned offset. And then we'll take our U offset and extract that. Good. So now we have the lowest 4 bits. Notice, however, that we're not grabbing bit 0. And there's a reason for that. I will have to defer the discussion of why that bit is not interesting. We'll come back to that, I promise, but not today. We have plenty of material to go through as it is. So let's see, the next field then is 10, 5. So now we need bits 10 or 5 through 10. And that is bit field 5, length 6. And then the next one is bit field 11. And then bit 12. So now we have extracted the pieces of the offset into small fragments, and now we have to reassemble them in different order. We'll start again with the least significant one. We'll take this bits 1 through 4, and what do we want to do with it? We want to put it at position 8. So we'll say uinster shift this stuff by 8. Then the next part is bits 5 through 10. They need to be placed at position 25. And then 7 is the position of bit 11. So we take bit 11 and put it at position 7. And finally, bit 12 goes in position 31. Okay, so having done that permutation, we now finally write our word. What a mess. What a horrible, horrible mess. Thankfully, the computer will keep the computer will keep track of all these bits for us, but it really is quite confusing. And the reason for this jumbling is explained in the RISC-V manual, but in short, this makes the hardware more efficient. So we're sacrificing a little bit of human readability of the machine code with for performance. Okay, so you run our test, and we get an error. What is the error, my friend? So we swap the order. Let's make sure this field here, which is containing 1.7, is this field, RS2. So if we go to our test, the 1.7 is supposed to go in the RS1 field. Which is, okay, so my mistake, I've swapped these inadvertently. We can fix that. Let's look at that again. So the 1.7, which is the RS1 field, should go right after or right before func3, according to the spec. There's RS1, which is 1.7, and then RS2, which is 2.1, should be up there. And the rest of the bits should be scattered as shown. Alright, so the bottommost bits are jumbled. So that is unfortunate. So let's make sure that our bit fields are correctly specified. Bit field 1 of length 4 bits. Bit field 5 of length 6, 25 ending at 31, good. Then this one is a 1-bit and that one is a 1-bit. So I'm fairly convinced that these bit fields are correctly specified. But now it is fully possible that my in the head calculation of those bit patterns is incorrect. I'm frankly tempted to just trust the output of the run here. Let's go ahead and just accept that this bit pattern is correct. In a later session, we're going to compare the output of our assembler to a known source which is known to be correct, and we'll see how well we do. But for now, we're going to make the assumption that this code is correct. Playing dangerously here, yes, but I believe in our bit field class more than I believe in my ability to mangle these bit patterns in my head. Oh, wait a minute. We did a mistake. There is a mistake because this should look like this, and then these. I'm in the wrong place. My apologies. This is where we want to be. Yeah. That looks a little bit more sane. Well, this should be bit 11, which should be a 0, but I'm seeing a 1. So that is a bug. That should be a 0. All right, let's go back and actually debug this. We'll go to the assembler, put our breakpoint here, and then run it under the debugger, and bit 11 should be a 0, is my contention. So let's look at these different bit patterns that we're extracting. Bit 11 should be a 0, but it's not, it's a 1, and bit 12 should be a so that does not make me happy. Let's add a watch point. We're going to say convert to int to string. We'll take the offset and we'll convert it to base 2. Let's see what that gives us. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Bit 12 should be a 0. Or we'll just satisfy ourselves with this pattern. It turns out that the bit field that we're encoding is actually 13 bits. Easily overlooked. But yeah, if you have a bit whose number is 12, then that means that the whole quantity is 13 bits. And so we should be putting a 0 here. But let's just keep it this way. It looks like the code is actually doing the correct thing. It's just that my test is incorrectly written. This is what it should be like. Let's try running this again then. And let's stop the debugger before we run the tests. Okay, fantastic. So I'm fairly certain that I did the right thing here, but now we have to confront jump and link, the final instruction for this session. And it's going to be more of the same. So let's go back to the assembler and let's see what bit fields we need for jump and link. It's going to be of the J type, so it's actually not that bad. It's quite similar to what we already did. So let's do that then. We'll need to create a bit field that extracts bits 1 and then of length 10. So let's copy this field. Length 10. Those are the 11 least significant bits where we ignore the least significant bit. Bit position 0 is not used. Then we go back and we grab the bit at position 11. We already have that bit field. It's this one, so we can reuse that one. Then we have a bit field starting at 12, and this one is 8 bits wide because it starts at 12 and the next field starts at 20. So this is 8 bits starting at 12. So starting at 12, we use 8 bits. And then finally, bit 20, a single bit. Nice. All right. So now we have enough to build a jump and link. So let's implement a jump and link assembler, and we'll put it here. And we'll create a new function, asm_j, and then a mnemonic for jump and link. Let's find that. Is this mess. And then it has a destination register, which I am going to hardwire. No, let's not hardwire it to 0. Let's make it the burden of the caller to pass the appropriate value here. There is no func3 for a J-type instruction, so we'll just proceed by putting our destination, which is remember the signed displacement from the current instruction that we want to jump to, and then we have this RD. Let's swap the order. So our destination field, that will be our destination register, and then we will have our SRC1, which is the actual offset, and there won't be a need for the last argument. So we can ignore SRC2 completely. Nice. Okay, so now we implement asm_j. So what it does, it has an opcode, and this is going to be the destination register. I'll call it RD to make it more clear, and this is our offset. Okay, so we'll start by filling out the resulting instruction with the opcode, the lower 7 bits, and then we're going to extract the pieces of the let's take the destination register and dispatch that, so we don't have to worry about that. The RD register is we'll place it at position 7, and so RD, put it at position 7. Now it's there, and then we grab the bit fields. So the bottommost bits are 10 through 1 of our. Actually, let's go back to the display up here because it's a little easier to read. So we want this field. We're going to encode this field first. So let's read that bits 1 through 10. And we'll do the same trick as before. We're going to take the offset, which is a signed number, convert it to an unsigned bit pattern, and then we'll grab that field, extract unsigned from the uinster, or offset, sorry, uoffset. And then the next is the bit 11, which we need to put at position 20. I'll wait with that though. We'll call that bit 11. Bit field 11, length 1. The next one is bit field 12. Bits 12 through 19. And that is bit field 12, length 8. Extract unsigned. And finally, bit 20. And that is going to be bit field 20, length 1. Did we not make a 1-bit? Yes, we did. Why so sad? Oh. Oh, capital L. Let's change that to be consistent. It's easier to read. Okay. So now we have the 4 fragments extracted from the offset, and now we're going to put them back in to the instruction that we're encoding. So let's take this. Let's see, jump. This is this piece first at position 21. So this is going to be bit field or bits 1 through 10. Put them at position 12. No, 21. Then we'll take our single bit 11, and he goes into position 20. And then bits 12 through 19 go to position 12. And then finally, bit 20 goes in position 31. So those are 21 bits scrambled together in order to save the world's electricity and computing time. Then we write the resulting word into memory, and we're good to go. So our unit test is going to fail, but let's assume that we've done our work correctly, and then we will fix this, or actually we will verify this against a known source that is correctly proven to correctly disassemble these instructions. Okay, so jump and link. You are not correct, sir. You want to be this value. We do see the 101010 pattern here. Oh, and that's because I am very sloppy. Let's fix this. So recall that we're going to put 0 here, and then we take the displacement, and the third operand we're just going to pass a 0 because we are going to ignore it. Nice. Alright, let's run the test again. And now we get this unhappiness. Yeah, it makes sense. So let's go to test results, grab this value, and put it in our unit test. It's this bit pattern. There's our 0 for our link register, and then this is the shuffling of our bit pattern for our displacement. Finally, all of our tests work, and now our assembler is able to assemble the program. But now we need to do the converse. We need to pick these bits apart and reconstruct these signed offsets to build or to be able to emulate this instruction properly. But we're going to save that until next session. So until then, thanks for watching, and I'll talk to you later.